We are live. So in this video, I'm going to go through the different examples that I provided on Compass. And so what we have is 4 different problems. And what I'm going to do is go through and solve all these problems kind of in this video in real time. So our first problem is a company manufactures 2 products. They have a price of or profit of $3 and $5 each. And they have to be assembled on a machine where product A takes 12 minutes of assembly time and product B takes 25 minutes of assembly time. And you only have 30 hours of time on the machine. And basically, you want to maximize your product. And you also have a technological constraint that where for every 5 products of A, you also have to make at least 2 products of B. And so the goal here is to kind of maximize the profit for this production company. And so let's go ahead and just kind of write this out. And I'm going to go through it step by step. So first, let's define our objective function. So we want to maximize profit. And we're going to take in a variable x. And what we're going to optimize is how many units of A do we make and how many units of B. So we're going to have A and B, and I'm going to unpack it from x. And then my profit, in this case, is going to be 3 times A, because I get $3 for every unit of A, plus $5 for every unit of B. And since I want to maximize, since I want to maximize the profit, right, what I'm going to do is minimize the negative of the profit. So I'm going to do minus 3 times A plus 5 times B. And that's going to be the profit that we're going to minimize. So the next thing we're going to have is we're going to have kind of our time constraint, right? And so again, I'm going to unpack my 2 variables just to make it a little bit easier. So I have my x and unpack it. And what we determine, so all constraints, so this is going to be an inequality constraint. And basically, all inequality constraints are non-negative, right? And so what this means is that at most I can use 30 hours. So what I'm going to say is 30 minus A, and each unit of A is 12 minutes times 60. So here I'm converting the minutes to the hour, plus, 25 plus B times 25 over 60. So what this is say is that the total amount of time that I dedicate to A and B will be less than or equal to 30, right? Because if I think about this minus sign, what I'm really saying here is that 30 is less than the sum of the time spent on A and B. But since it's just simply written as a non-negative constraint, and what's implied here, of course, is that this is all greater than or equal to 0, but we're going to take that away. And so that's our time constraint. And then we have our tech constraint. So this is our next one, right? And so again, we're going to have A and B is equal to x. And here what we're saying is for every unit of A, we need to make at least 2 units of B. The way I would do this is B over 2 minus A over 5. And what we're really saying here is that B over 2 must be greater than or equal to A over 5. Way I think about it is that if I have 5 units of A, then this will become 1, which tells me that B over 2 has to be bigger than 1, and that'll be only true if B is 2 or greater. So that would be my second constraint, right? Then I'm going to have some bound constraints, right? And basically, I want both of these variables to be non-negative because we can't make negative values of units, but I'm not going to put an upper bound there, right? Because I don't know what the maximum is. Technically, it's going to be determined by the total amount of time you have, but we can leave that unbounded. And so then we add our constraints, which again, where we have our constraints, and this is a list of a dictionary. So we do our type of our constraint. And in both these cases, our constraints are going to be inequality constraints, and then we tell it which function we have. And so our function for the first one is going to be time. And then for our second one, we're going to again have a type. We're going to have an inequality constraint. And then the function in the second one is going to be our technical constraint. So then I can go ahead and solve this. So I'm going to do minimize. I'm going to minimize the profit. My guess, since I have 2 variables, I'm just going to pick 1, 1. And then I'm going to do bounds is equal to BNDS, and then constraints is equal to cons, right? So here I'm passing in the functional constraints, and here I'm passing in the bounds on the variable. So I run this. Minimize is not defined. Did I forget to run this up here? Let run this. Let's see if this works. I get a solution. And so what I can do here is I can print and I can say A is equal to percentage G. And my first one is sol.x of 0. And then I can print my second variable. Well, got ahead of myself. I get B is equal to percentage G. And then I'll do percentage sol.x of 1. And then if I want to do my profit, I'll do again 0.2f or percentage 0.2f. And here I'm going to pass in minus sol.fun, right? Because remember, when we want to maximize something's equivalent to minimizing the negative of the function, and then we got to negative it again. And so here we run it, we find out the optimum solution is 81, make 81 units of A, 32 units of B, and we'll have a profit of $409. Typically you would just round these down because you can't make fractional parts of A and B, but here we've kind of solved this optimization problem. All right, so our next one is a diet problem. This is actually another classic problem in optimization where you have something and you want to mix things together and those mixtures have to satisfy certain properties. So here you're going to make a feed composition and we're going to make it from corn and soybean oil. We want to minimize the cost. We want to make at least 800 pounds of this stuff. And we have certain requirements on the protein and fiber. So we'll start off with the cost. So we'll define the cost. Again, I have two variables here. So I'm going to have corn and soy, which I'm going to unpack from the x. And then my cost, and since this is going to be easy since I'm just doing a minimization, so it's just going to be 0 times 3 times corn plus 0.9 times our soybean oil. So that's kind of our minimizing our cost, and this is what we're going to minimize. So next we have our different constraints. So the first one is we have kind of our total constraint, which I'll call it just total. You can name these anything you want them to be. So we have corn and soy. And what it's saying is that the mixture of corn and soy, we have to make at least 800 kilograms of it. And so here, corn and soy, this is all on a kilogram basis. I wasn't clear about this. So basically, this is the fraction of protein, and this is the cost per kilogram. All right, so what we're going to have here is we're going to have return. Remember, it's a non-negative constraint. So what we're saying is that corn plus soybean has to be bigger than 800. And that's going to be kind of our total one. This is going to guarantee that we make at least 800 pounds of a mixture of corn and soy. And then we can do our protein, which is our next one. And so this is how I'm going to do it. So corn and soy X, we're going to unpack it. So what we're saying is that we have to have at least 30% soy, 30% protein. So if we take the mixture, right, that's corn plus soy, right, that has to be, at least this part has to be bigger than 30%. So when we take the mixture of it, we know that for every kilogram of corn, we're adding 90 grams of protein plus 60 grams of protein or 600 grams of protein for kind of the corn part or the soy part. So what we're saying here is this corn is contributing 0.9 protein, soy is contributing 0.6 kilograms of protein. This is per kilogram of corn and soy. When we mix these together, the total mixture has to have at least 30% protein. And so this is how we'd write this constraint. Another way you could think about this is if you divide through by this corn and soybean, this equation would give you also another way of getting that percentage. So that would be the at least part. And then we're going to have the fiber part. And so we don't want a certain amount of fiber. So we have corn and soy again with X. And so here what we're going to say, so we have our fiber of 0, our total fiber here, so is going to be, where do I go here? So we have 0.05 times corn plus soy, right? All right, so that's kind of our maximum value, right? Because that'll be the fiber. And since this is going to be an upper constraint, we're going to do minus 0.02 times corn plus, minus, let me bring it over here, put a parenthesis around that, plus 0.06 times the soy. So that would be the fiber content. So this is the total when we mix it together. And that's kind of the upper bound. And so then we add these. This is the contribution of soy, contribution of corn. this mixture has to be less than 5% of the total amount of fiber. Hopefully that's clear with that part. And so then the last part is we're going to do our bounds on our variables, just as before. I keep on hitting this mute button. But again, we have 0 for the lower bound and no upper bound. And then we have our upper bound. And then we're going to do our constraints. And let me just grab this code up here just to make life a little bit easier so I don't have to retype everything. And so my first constraint is going to be total, which is an inequality constraint. My second one is going to be the protein, which is again an inequality constraint. And then my third one, let me just copy and paste this, is going to be my fiber constraint. And then when I'm done, I can print, corn is equal to percentage G, and then that's going to be sol.x of 0, and then print the soy part is going to be percentage G, and this is going to be percentage sol.x of 1. I also have to change this. The objective function, we called it cost, not profit. I made that mistake a couple times. And then the final thing we want to do is put the cost. And since we're just minimizing something, we just put the value in. We don't have to minus it or anything like that. And then we're going to do percentage sol.fun. And so I run this. And of course I have a where do I have soy? There's the typo. So that's soy. I run it again. And I find my optimal solution is 470 kilograms of corn, 329 kilograms of soy. Together, these will satisfy the protein and fiber content. And then the last one is the cost, which in this case is 437. So hopefully these constraints are clear, like the protein constraint and the fiber constraint. Another way you can think about this is we could have also done return 0.09 times corn all over corn plus soy, kind of your total, plus 0.06 times the soy fraction, right, plus soy. Together, their two contributions have to be bigger than equal to 0.3. But what I've done is made this kind of nonlinear constraint, and I've multiplied top and bottom by corn plus soy, which kind of gives me this expression. So that's another way of thinking about that constraint. All right, problem number 3. So this is a blending example. This is actually a classic problem in optimization. It was one of the first commercial uses of optimization. So the idea here is we have 3 stocks of gasoline, so 1, 2, 3, with an octane rating of 70, 80, and 99. We have different availabilities for it. They have different prices, and we want to blend these together so we get 2 different kinds of gasoline. And we want to determine how much of gas 1A should we make and how much of gas B should we make. And so the key thing with these blending problems, and this is going to be similar to kind of your cutting example problem of the rods, is that rather than optimizing over stock 1, stock 2, stock 3, and gasoline A and B, we're actually going to optimize over the flow of how much stock 1 goes to A, how much stock 1 goes to B, how much stock 2 goes to A, how much stock 2 goes to B, how much stock 3 goes to A, and how much stock 3 goes to B. So these are kind of what I think is flows from the different stocks to our gasoline. So kind of setting this up, we're going to start with profit. We're going to take in X. And now we're going to have 6 optimization variables. So we're going to have stock A to A, stock 1 to A, and then stock 1 to B. And then we're going to have stock 2 to A, and then stock 2 to B, and then stock 3 to A, and stock 3 to B. And we're going to use that to unpack our X variable. And so our sales, so I'm going to break this up in a bunch of different points. So our sales is going to be based on a gasoline price. So it's going to be 37.5. And it's going to be now the total amount of stock A that we make, which is how much stock 1 to A plus stock 2 to A plus stock 3 to A. So that's the total amount of A that we make. And then we can do the second one, which is 28.5. And that's going to be stock 1 to B plus stock 2 to B plus stock 3 to B. So that's going to be our sales. And then our cost is going to be dependent on how much of the stock 1, 2, and 3 to use. So first it's going to be 9 times the amount of stock 1, which is stock 1 to A plus stock 1 to B. And then let me put a new line between here, plus the amount of stock 2 that we use. And I forgot to put a 1 there. And then we're going to have plus 12.5 times stock 2 to A plus stock 2 to B. And then we're going to have plus 27.5, which is going to be stock 3 to A plus stock 3 to B. And so basically, this is the total amount of A that we make, and this is the total amount of B that we make, and this is the total amount of stock 1 that we use, this is the total amount of stock 2 that we use, and this is the total amount of stock 3 that we use. And then we're going to return, since it's a minimization, we're going to minimize cost minus sales, which is basically the negative of the profit. Let me put an S there, and let's make sure everything goes right there. All right, so that's what we're trying to optimize. So our next thing is I'm going to put in the constraints for availability. And so what we can do is define stock 1 of X. And what I'm going to do is just grab all this. So I'm unpacking the same variables in every single function. I can just unpack it right there. And let me correct the indentation. So what we're saying here is that we have at most 2,000 barrels of stock 1, or I don't know if it's gallons, any given unit. So let's just say it's gallons. And so again, it's a non-negative constraint. So we're going to have 2,000 times stock 1, the amount of stock 1 that we put to A, plus the amount of stock 1 that we put to B. So that's our first constraint. And let me put this as stock 1. And then we can do the same function. Actually, I'm just going to copy and paste this. So I'm going to have stock 2, and then I'm going to have stock 3. And so stock 2, we have a maximization of 5,000, right? So that's the maximum value. And then I'm just going to put 2 and 2 here. And then for stock 3, I have a maximum of 3,000. And is that correct? Yeah, 3,000. And that's going to be stock 3 and stock 3. So that's going to be kind of our 3 stock variables. Here we're saying the amount of stock 1 is at most 2,000. Amount of stock 2 is at most 5,000. And the amount of stock 3 is the most 3,000. So the last constraint is that we have an octane rating. And this is going to be similar to what we did with protein and fiber, right? So we got to have like a minimum octane rating. And I'm going to do these as inequality constraints and say that we're going to make that our gasoline A and gasoline B have to have an octane rating of at least 93 and 85 respectively. And basically the octane is going to be the linear combination of the octanes from the stock. So we'll define first octane of A of X. And again, I'm going to unpack the variables, right? And so I don't want to retype this. And so what we're going to say is that the total amount of A that we make is stock 1 to A plus stock 2 to A plus stock 3 to A. And so as we did before, we see that stock 1 to A contributes an octane rating of 70, plus stock 2 is 80 times stock 2 to A. It's going to give us an 80 plus 99 times stock 3 to A. And that has to be bigger than 93 times the total amount of A that we make, right? So this is kind of the constraint that the mixture of these 3 things, when they get combined, they'll at least have a value that's bigger than 95, or 93, I'm sorry. And then the same trick with octane B, right? And so in this case, our total amount of B that we make is equal to stock 1 to B plus stock 2 to B plus stock 3 to B. And then the amount of B that we make, we need a minimum octane rating of 85. And then I'm just replacing the B's here. So that's a B, and whoop, that's a big B, and that's a big B. And so I think I have all that right. I didn't get an error yet. I'm sure I'm going to get one once I run it. So the key thing is we have 6 decision variables, and those 6 decision variables are the flows from the stocks to the stock 1 to A, stock 1 to B, and so on. So now we can define kind of our optimization problem. So we'll do bounds. And so I'm just going to do non-negative constraints on the bounds. And so here's a short way to construct that. So I'm just going to do 0 times none. And then I'm going to repeat it 6 times. And that's going to basically, if I take a look at bounds here, that's going to give me 6 bounds kind of replacing where the minimum 0 and I don't have any upper bound. Next thing we got to do is assign our constraints. And here I'm just going to grab this up here because I don't want to retype this. And if I look at my first constraint, it's octane of A. And these are all inequality constraints. So that's octane of A. Here we have octane of B. And then our next one is going to be stock 1. And then I can copy this. And then I have my second one, which is stock 2. And let's create a new line. And then we're going to have our next one, which is stock 3. So these are our these are our constraints where we have 5 different functional constraints. In addition, we have non-negative values on kind of our decision variables. So now I can minimize it. Let me just grab this up here and come down to this part. And what we have now is everything's the same except we have 6 decision variables. And so I have no idea what to guess. So I'm just going to guess 1s and I'm going to guess 6. And let's see if that runs. Oh, I want to minimize the, what did I call this function up here? Profit. So that's what my minimization is. So that's profit, right? And so that works. And so then I can unpack it, right? I'm actually going to grab this variable up here. And so if I want to unpack it, I can just say all these different variables is equal to sol.x. And then the total amount of A that I make is the amount of stocks going to A. And then this is kind of stock 1 to A plus stock 2 to A plus stock 3 to A. And I put an extra space there. And then the total amount of stock 1 that I make is stock 1. That's a big A is stock 1 to A plus stock 1 to B. And then stock 2 is equal to stock 2 to A plus stock 2 to B. And then I have my third stock, which is stock 3 to A plus stock 3 to B. And so then I can print and I can say A is equal to percentage G. And I'll put my A there and then I'll do print the amount of B that I make is percentage G. And then I can do the amount of B that I make, and then I can say how much of the stock 1 do I use. So stock 1 and is equal to percentage G, and then I can do stock 1. And then I'm just going to copy and paste this 3 times, or 2 times. 1, 2, and that's going to be 3. That's 2. That's 2 and 3. And then I can do my profit. Print profit is equal to percentage 0.2f. And then again, it's going to be minus sol.fun since we're trying to maximize something, so we minimize the negative of that function. And I look at the example, and in this case, I'm actually not going to make any A. I'm solely making B. And basically, I'm using up all of stock 2, all of stock 3, and a little bit of stock 1. And my maximum value is 105,000. And that's how much I make. It's very common in these kind of mixing problems or these allocation problems. So this is where kind of allocating different stocks to gasoline blends, is that often you're going to find that some of your solutions, so some of the potential products are 0. So this is very common in optimization, particularly when we have linear constraints, which is what's known as linear programming. All right, so let's do this last one. And so this is a loan problem. And so what we're trying to do here is we got basically $12 million that we can loan, and we have different interest rates, and we want to maximize the interest rates, minimize kind of the probability of debt, and then we have all these different constraints here, and I'll just go through them one by one. So let's first define profit. And so we're going to unpack this as before. So personal loans, car loans, home loans, farm loans, and then commercial loans. And that's going to be equal to x. So what I'm going to assume all these variables are is the amount we loan to each in terms of $1 million, since that's kind of a unit and no other units were given. And so then I'm going to return, and I want to maximize the profit. So I'm going to put a negative in front of the quantity I want to maximize. So it's 0.14 times personal loans. So these are like credit card loans, which have high interest, same with car loans. And then you see that home loans are a little bit cheaper, right? Typically because you have the collateral of your home. That's a pretty high home interest rate, though. Then you have farm loans, 0.125 times farm. And then we have 0.1 times our commercial. All right, so that's what we're going to maximize, or in turn minimize. So the next one we're going to do is we only have $12 million. So let's do our total constraint. And so again, let me unpack this. And so the way we're going to do this, we're going to just do all inequality constraints here. So we're going to say the maximum we can spend of personal, we can lend to personal plus car plus farm plus home plus farm plus commercial is equal to 12 million bucks. All right, so now we have some bunch of other ones, and we can assume this one, bad debts are assumed unrecoverable, hence have no interest rate. So we're going to leave that assumption out and make it a little bit easier. But so now we have this competition constraint. So competition with other financial institutions, the area requires that we allocate at least 40% of the total loans to farm and commercial. And so I'm going to do this as constraint 1 because I don't know what else to call it. So again, I have my 4 variables. And to make life easy, I'm going to say total. So this is the total amount of loans that we make is equal to personal plus car plus home plus farm plus commercial. So what we're saying here is that if we read this, that farm plus commercial has to be greater than 0.4 times the total. That's another way of putting it. And then our second constraint is that to assist the housing industry in my region, the home loans must equal at least 50% of the personal, car, and home loans. All right, so that's going to be our second constraint. And so again, we're going to unpack all these variables. Oop, unpack the wrong thing. So let me come back up here. And let me just read this correctly. So here's our unpacking part. So I'm saying that home loans must equal at least 50%. So home must be bigger than 0.5 times personal plus car plus home. And so that would be my second constraint. And that looks right. And then the last one is my bad debt. So this is bad debt, and I'll just call it bad. And here what we're saying is the stated policy that the overall ratio of bad debt for all loans cannot exceed 0.4. And so here's the probabilities. And actually, I'm going to move this up here so I can read this up here. So I can define bad. Again, I'm going to pack everything. And what I'm going to do here is, again, using this total term. So here I have the total loan. And so what I'm saying is that return is that 0.4 times total is going to be bigger than the different bad debt probabilities. So 0.1 times personal plus 0.07 times car plus 0.03 times our home loan plus 0.05 times farm and plus 0.02 times commercial. And so that's going to be our second. So, the total, the bad part of it has, basically we're kind of doing mixtures. So these are just kind of additive constraints. So then the rest of it is just basically what we did before. So what do we have? 1, 2, 3, 4, 5 decision variables. So let me just grab all this up here because I don't want to retype everything. So I have 5 bound constraints. And then my constraints are, my first one is bad. My second one is total. My third one is what I'm calling con1. And then my second one is con2. And then I get rid of this. And then I have 5 initial guesses. And let me just clear this out right here. Right, so I'm minimizing. Yeah, I got profit. That looks right. Let's see if this runs. All right, I got bar. Oh, that's bad. All right, let's see if this runs. All right, so it ran. So again, I'm just going to unpack everything. So I got personal, farm, and X, and so that's sol.x. And then I can do personal. Actually, I'm going to make this a million, so I'm going to just do 1e6 times this. So that's going to take everything converted to dollars. Is equal to percentage 0.2f. I actually put a dollar sign here. And that's going to be commercial. And parenthesis sign here. And then I'm just going to copy these. Let's see if that works. Yep. Oh, nope. Oh, I got it wrong. That's personal. See if this gives me an answer right. And yeah, so I got some numbers here. I got personal. I got 3, 4, 5. So I got car. I got home. I got farm. And I got commercial. Commercial, and let's do it over here. I got car. I got home. I got farm. And I got commercial. And the last thing I have is profit. So print my profit is, and this is going to be in millions, percentage G, percentage 0.2f, 2f, put a dollar sign in here. And then what I want to do, I have to also multiply this by 1e6 times minus sol.fun. And so I get my profit, and let me check the answer, make sure I got it right. Yeah, so I got $147,000. It seems I make no commercial loans. I make a lot of farm loans, a lot of home loans, no car loans, and a bunch of personal loans. So that would be kind of the solution for this problem. Again, these kind of constraints, typically I reason through them, but in these kind of mixing problems, basically all these problems would seem we're just mixing things together and then putting constraints on the compositions like upper bounds or lower bounds on those compositions. All these problems fall in the general category of what's known as linear programming. That's just a fancy word for linear optimization. And these are fairly common in kind of business decisions in industry, and particularly in the chemical engineering industry. Hopefully that's all clear. I've also posted this code on Compass. If you have questions, as always, put them in the comment section, post them to Piazza. And I apologize for being late with the videos this week. All right. Bye, everyone.